Lesson 3.4, Placebo Effect and Blinding. Our objective for this lesson is to be able to determine whether single or double blinding is necessary for an experiment. First, let's talk about a placebo. So a placebo is a substance or treatment which is designed to have no therapeutic value. So an example of a placebo is something we often call a sugar pill. So a sugar pill is something that's designed to look like the drug that is being tested, but actually will have no physical effect on the body. And the reason that we have this, the reason we introduce placebos is something called the placebo effect. So the placebo effect is the situation in which patients improve simply because they believe they are receiving a useful treatment. So what we want, if we're testing a drug, for example, we want to make sure that any improvement that we see is caused by the active ingredients in the drug that we're testing and not by the psychological impact of someone's health improving just because they think that they've been given a cure. So we're trying to test that physical impact and not some psychological impact, which is what's known as the placebo effect. So an experiment is often blinded. So we will blind an experiment in order to make sure that that the participants or the researchers or both do not know whether they're in the treatment group or in the control group. So an experiment is single blind if the participants do not know whether they are members of the treatment group or members of the control group, but the experimenters do know. So for example, if we're testing a drug, then the treatment group would get the actual drug. The control group would get a placebo, so that none of them know whether they are in the treatment group or the control group. They know they took a pill, but they don't know whether it was the actual drug being tested or a placebo. Now, for some experiments, it's important to do a double-blind experiment. So a double-blind experiment is one in which neither the participants nor the experimenters know who belongs to the treatment group and who belongs to the control group. So this is to, for example, if we give the treatment group a treatment and we give the control group a placebo, but then there's some sort of interview that follows or some sort of observation that the experimenters are making. We want to make sure that the experimenters don't see something that's not really there because they're looking for an effect in the treatment group. So sometimes we want to know, we want to make sure that neither the participants nor the researchers know who belongs to the treatment group and who belongs to the control group, and that's a double-blind experiment. For our first example, we're given an experiment that asks whether vitamin B6 improves a person's ability to play the violin. And we're asked to identify a control group, a treatment group, and to comment on whether double or single blinding would be necessary for this experiment. All right, so there's a few ways that we could run this experiment, but let's say that we want to have two separate groups. Well, we would want to make sure that everyone in the group has the ability to play the violin and that they're all have a similar ability level. And then once we choose a sample of violinists with a similar ability level, we'd want to randomly separate them into a control group and a treatment group so that we're not putting all the best violinists in one group and the worst violinists in another. But once we've done that, the treatment that we're trying to apply is vitamin B6. So we'd want to put those folks in the treatment group are going to get vitamin B6, and the folks in the control group are going to get a placebo. So the treatment group would be violinists who are given vitamin B6. And they may be given this vitamin over a period of time to allow that to build up in their system. But then after they've been given this vitamin B6 treatment, they will be asked to play the violin for our researchers to determine whether it has improved their performance. And the control group would be violinists who are given a placebo. Okay, so now is blinding necessary? Well, yes, blinding would be necessary in this experiment. And we can see we've given the control group a placebo in order to facilitate that blinding so that these violinists don't know whether they're in the treatment group or the control group. And that's going to be important because if they feel like they've been given something that is supposed to help them play the violin, they may unconsciously play a little bit better. And we want to eliminate that by not letting the participants know whether they're in the treatment group or the control group. Now, would we want the experimenters or the researchers to know who's in the treatment group and who's in the control group? And I don't think we would want that either, because how well someone plays the violin is subjective. And so if the researchers are judging who played the violin better, they may unconsciously see some improvements in the treatment group that they don't see in the control group. And so even if they're not there. So we would want this to be a double-blind experiment. We wouldn't want either the participants or the researchers to know who was in the treatment group and who was in the control group. In our second example, we're given an experiment that asks whether adding phosphorus to fertilizer makes crops grow faster. And we're asked to give a control group and a treatment group and to comment on whether blinding, either single or double blinding, would be necessary. All right, so for the treatment group and control group, we're testing whether phosphorus in fertilizer helps the crops grow faster. So the treatment that we're wanting is phosphorus in our fertilizer. So the treatment group would be crops that are given fertilizer with phosphorus. And now our control group then would be crops that are given fertilizer without phosphorus. Notice here that what we're testing is not whether or not fertilizer has an impact. So we're giving fertilizer to both of these crops, or to crops in the treatment group and crops in the control group. The only difference is that the treatment group, their fertilizer has phosphorus in it, and the fertilizer for the control group does not have phosphorus. That way, the treatment group and the control group are completely the same. The only difference is this phosphorus. That's the thing that we're trying to test. So then we know that if we see the treatment group crops grow faster, we can infer that that is because of the phosphorus in the fertilizer. All right, so now do we need some sort of blinding with this experiment? Well, we certainly don't need the crops to not know whether they're in the treatment group or the control group. They're plants. They don't have any idea of what phosphorus is or what's happening to them. So we don't need to keep the plants in the dark. This is strictly a human thing. So there's no need for the crops to be blinded in any way. And I don't think there's any reason for the researchers to not know either. They're going to be able to measure the growth of the crops in an objective way. It's just we're just measuring these plants, and there's not any judgment call that's going to be influenced by them knowing which crops had the phosphorus fertilizer and which had the non-phosphorus fertilizer. So for blinding, we're just going to put no here. This experiment is not one that needs to be blinded.